in the Cartesian plane, where the horizontal axis is called the x-axis and the vertical axis is called the y-axis, a point on this plane is represented by a pair of numbers called the x-coordinate and the y-coordinate. And we all know that the x-coordinate represents the horizontal distance from a fixed point. Let's represent it as a dot. This is the origin. And y, the y-coordinate, represents the vertical distance from the same fixed point from the origin. Then whenever we go across and whenever we go up, we have exactly the point x comma y in the Cartesian plane. But there is also what is known as the polar plane. For example, there are such things as polar coordinates. So let's go ahead and figure out exactly what that means. Let me label this diagram here as Cartesian plane. And what we want to do right now is to figure out what is a polar plane and then what are polar coordinates. The polar plane consists of a fixed point called the pole, and it consists of a ray typically pointing in the right direction like this. Let me label again. The fixed dot is called the pole, but for simplicity, it is okay to call it also the origin. And this ray right here, it is called the polar axis. So this is the polar axis. And again, the polar axis doesn't have to always point towards the right, but for the point of convenience, for the point of somehow matching the positive x-axis of the Cartesian plane, it is usually represented in this way. You're going to see that whenever we get to graphing polar curves, it is very convenient for the polar axis to point towards the right, as the positive x-axis does as well. A point on the polar plane. Let's take this point right here. Let's label it point P. A point on the polar plane is not defined by how far away horizontally it is from the origin or vertically. That doesn't exist on the polar plane. The way in which a point is defined on this plane is by figuring out what is its distance from the origin, from the pole. Typically that distance is represented by r, and by figuring out the angle that is formed from the polar axis to the ray that connects the pole and the point. Let's actually label the pole as O. So this angle right here that is formed, we're going to call it theta. So the polar coordinates of point P are represented by two numbers. R goes first, and then theta goes second, and they're separated by a comma. Here R is called the radial coordinate, and theta is called the angular coordinate. And these two coordinates tells you exactly how to find point P. It gives you its distance from the pole, so from point P to the pole O, and it gives you the angle that is formed from the polar axis towards the ray formed by the pole and point P. And theta follows the same convention as any other theta that we have defined since grade 11. So we know that if theta is measured counterclockwise, theta is positive. But if theta is measured clockwise, then theta is negative. And theta is always measured from the polar axis, always. And it goes around the pole. Again, counterclockwise, positive, clockwise, negative. Here I represented the same diagram above. It was just too much going on with all of these names. So I just have the pole, the polar axis, I have point P. What I want to note is that I can go ahead now and create another point, represent another point. Let's call it point Q. Now, point Q could be somewhere here, for example. So this is going to be point Q. And again, if I want to locate point Q, I have to measure its distance from the pole. Let's call it in this case R prime. And then I have to measure its angle, the angle that is formed from the polar axis. We're going to call this angle theta prime. So then the coordinates of point Q are going to be R prime, comma, theta prime. And that's how I can easily locate point Q. Now, how will the polar grid look? We know how the Cartesian grid looks, right? If we have over here the y-axis, we have the x-axis. The Cartesian grid looks exactly like a square grid. It is full of tiny little squares, right? Because we locate a point on the Cartesian plane by looking at its horizontal distance from the origin and its vertical distance. Everything is very straight, right angles, horizontal versus vertical. But a polar plane doesn't look squarish. It looks more circular. And that's because of the rotation that goes on with theta. For example, imagine, I'm going to switch the color here to something a little bit gentler. Let's say all the points that are R prime away from the pole, R prime away, all of those points are going to fall in this circle whose radius is R prime. I don't know if you can imagine that. I know it's not a perfect circle, but okay. So all of these points, all the points that fall on this yellow circle, they are the same distance away from the pole. What changes is theta prime. Theta prime is different from different points on this circle, but they are all the same distance away from the origin. Similarly, if I draw the circle that passes through point P, let me choose a different color. If I draw that circle, all of these points on this orange circle are going to be the same distance away from the pole. So I'm hoping that you're getting the point that a polar plane doesn't look squarish. It looks more circular like this, right? And then you always have the polar axis originating from the pole and moving as a ray towards the right. So the polar plane looks circular. The Cartesian plane looks squarish. I'm going to go ahead now and give you a very nice picture of a complete polar grid. Here you have the nice polar grid. You can really see over here, the center is the pole. Look at the polar axis right here. And you can now look at all of these radial axes. One starts at pi over 12. I actually have them both. I have the angles measured in radians and degrees, But the understanding here is that an angle is always measured in radians. And so I have one ray at pi over 12. You can call this ray a radial line if you want to. I just like to call it a ray sometimes. Here I have another ray at pi over 6, pi over 4, and that's how I go all the way along my plane. And then I also have these tiny circles. This circle here is a circle with radius 1. It is impossible to draw every single circle with every single radius. So the understanding is that if you're talking about a circle with radius 1.5, you're going to approximate it by being somewhere here. So practically I have only drawn the radiuses that go 1 unit at a time. So this is over here radius 1, radius 2, 3, 4, 5, 6, and so forth. And whenever you consider those circles together with the rays, you have a complete polar plane. So that's what we have right here. Let's go ahead and take a random point. Let's say this point right here, okay? As usual, we can call it point P. The coordinates, the polar coordinates of point P are going to be, in this case, r comma theta, but r represents its distance from the pole, so this length right here. And the way that I figure out is by counting a unit at a time. So this will be 1, 2, 3, 4. That means that the radial coordinate will be 4. And the angular coordinate is exactly angle theta from the polar ray counterclockwise towards P. So then that angle is going to be right here, pi over 6. So these are the polar coordinates of point P, the point that I just randomly chose. What I want you to notice right now, probably some of you are already thinking about it, is that this is not a unique representation of point P. This is not the only representation of point P. This is what is different from the Cartesian plane. In the Cartesian plane, a point only has one representation, x comma y. X comma y is unique in the Cartesian plane. In the polar plane, that's not the case. 4 comma pi over 6 is not the only representation, and that's because there are infinitely many other angles that are coterminal with pi over 6. I can go one complete revolution, so 2 pi and then pi over 6. I can go 2 revolutions and then pi over 6. I can go the other way around, let's say clockwise, and I have this angle right here. So then a point P on the polar plane has infinitely many representations. So representations in the polar plane of a point are not unique. Another way then that I can represent this point right here is to say, again, the radial length is going to be 4, but then the angular coordinate will be pi over 6 plus 2 pi k, where k is an integer. That means in the general case, if we pick a point P with polar coordinates r comma theta, then that implies that the other representations of point P are going to be r. R doesn't change, right? R represents the distance from the point to the pole. That distance is always the same. But what changes is the rotation of the angles. Theta changes. So we can express theta as theta plus 2 pi k. Oop, my pi looks strange. 2 pi k, where k is an integer. By letting k be an integer, then I am allowing K to be positive, to be negative, and that's how I get all angles that are coterminal with theta. Another thing that we have to go over is the fact that in the polar plane, R can be negative. In the Cartesian plane, R always represents a positive number, but in the polar plane, we can work with a negative R. So, for example, I want to go back to this point right here on the polar plane, point P. Point P, we said, is R units away from the pole and theta radians away from the polar axis. So let's label this as theta. If I now consider the polar coordinates negative r, comma, theta, this will no longer represent the same point P. This will represent a different point. Let's call it point Q. Notice how theta doesn't change. I am considering this point Q that has the same radian measure for theta. Theta is not changing. These thetas over here, actually I should make that really clear. This theta and this theta are identical. So based on my polar grid right now, based on where I located P, theta is, for example, pi over 6, if you want to give it a value. Pi over 6, and right here, pi over 6. So I am not changing theta. What I am changing is r. Here, r is positive. Here, r is negative. So this is how you're going to go ahead and you're going to find point Q. Let me even actually do it here separately. Here is the pole. Here is the polar axis. We said that point P is going to be r units away from the pole and then theta radians away from the polar axis. So this is really P. If I want to locate Q, what I am going to do is I am going to go ahead and measure again theta. Theta doesn't change. But instead of moving upwards, I am going to move downwards in the opposite direction. So please imagine that you extend this ray in a straight manner like this. And now what you're going to go ahead and do is to measure R units. So if this is R, you're going to measure R in the opposite direction. That looks about right. This length seems to be identical to this one right here. So practically then, this is negative R because you went in the opposite direction as before. And once you measure this length over here, then you have located point Q. Point Q will have coordinates negative r, comma, theta. So whenever you have a negative length, the point that is represented by that negative length doesn't fall in the same place as theta. You're going to go ahead and measure theta counterclockwise if theta is positive, but instead of going up r units, you're going to go down in the opposite direction r units. And again, this line over here should be completely straight. So then that means that this angle right here is pi. So here I have point P with coordinates r, comma, theta. And here I have point Q with coordinates negative r, comma, theta. I do want you to notice though that I can express point Q in the traditional sense with a positive r. But if I change my r to a positive r, then the angle will no longer be theta. The angle is going to go from the polar axis counterclockwise, boom, all the way to this ray right here. So then another way that you can express the coordinates of point Q are going to be in the traditional sense with a positive r. So then that means that my angle is going to go all the way up to that ray. So then the other coordinates will be positive r if I want to keep my r positive, but now the angle is not going to be theta. It's going to be theta plus pi, right? This is the traditional way to represent a point in the polar axis with a positive r and with your angle in counter clockwise motion or clockwise motion. Before I continue with examples, however, why don't we go ahead and right now note what are the coordinates of the pole? After all, the pole is a point. So then, remember, in polar form, a point has coordinates r, comma, theta. So for the pole right here, if I want to denote the coordinates of the pole, r is going to be 0 because we are at the pole. So the distance of the pole from itself is going to be 0 if you want to think about it that way. So 0 right here, theta can be anything pretty much. I don't care. As long as r is equal to 0, I am denoting this point right here, the pole, the origin. So the pole or the origin has coordinates 0, comma, theta. 0 representing the distance of the pole from itself. Example 1 is asking us to plot the following points on the polar plane. So here is my polar plane. Point A has coordinates 1, 5 pi over 4. So then r is equal to 1, and we know that theta is equal to 5 pi over 4. The first thing that I'll do is to locate the ray that corresponds to 5 pi over 4. And if you notice, it is right here on the grid. No, I'm actually lying. Right here, 5 pi over 4. Now, what I want to do is to find the circle with radius 1. So then that circle is going to be this tiny, the most inner circle right here. That means that my point is going to lie at the intersection of this circle and that ray that corresponds to 5 pi over 4. Here is my point. So let me go ahead in a very small way and put over here, this is theta. And then from the pole down, this is going to be 1. Now we're going to go on to B. So for B, we know that r is 2, and we know that 3 pi is going to be theta. 3 pi. That means that we went 1 complete revolution plus pi, or rather pi plus a complete revolution. Maybe that's a better way of thinking about it. Now the radius is going to be 2, so this is 1 right here and this is 2, and then theta, the theta involved is 3 pi. So the way that you would denote that is really by going 1 complete revolution and then boom, pi right here. So this will be the point. This is the point with coordinates right here, 2, 3 pi. All right, now let's do C. C right here has, one pen, okay? C right here has an r that is 2 and has a theta that is negative 2 pi over 3. Since the angle is negative, then that means that we're going to measure the angle clockwise. we're going to go over here from the polar axis all the way to negative 2 pi over 3. Negative 2 pi over 3 is in degrees equivalent to negative 120 degrees. So remember that these radial lines are going by 15 degrees. That means that we have to go negative 90, and then we have to go 15 degrees, another 15 degrees, so 30 degrees, and that's how we're going to find negative 120 degrees. That means that we're going to be right here on this radial line. So let me label that. It's going to be right here as negative 2 pi over 3. So right here, meaning that we're going to go a unit, an r equals to 2 units. So 1 and 2. And we're going to represent the angle by drawing our little curved arrow, but in the clockwise motion, because this will be negative 2 pi over 3. So this is the point from part C. Finally, part D. Now we have over here in part D that r is negative 3, and we have that theta is 3 pi over 4. So the first thing that I want to do is to locate 3 pi over 4. Notice right here, this is 3 pi over 4. So if r was positive, I would go 1, 2, 3. But because r is negative, I measure in the opposite direction along this radial line. So I am going to go, let me even mark the ray or the line right here. It's going to be like this. So from the pole, I am going to measure 1, 2, and 3 right here. So this is where the point is going to be. I will still write this as theta, 3 pi over 4, but now this length right here, this one right here, I know that you can't see it very much, so this one right here is going to be negative 3. So if you want to label, you label this length as r equals negative 3. So the coordinates are going to be negative 3, comma, 3 pi over 4. So again, if r was positive, I would measure upwards 3 units. But because r is negative, I measure along the line that passes through the pole and is directly opposite. I really draw a line. And then I go in the opposite direction 3 units away. 1, 2, and 3. So the polar coordinates are negative 3, comma, 3 pi over 4. However, rehearsing, if somebody were to ask you, can you represent this point with traditional coordinates? So that means with a positive r. Then you know that immediately with a positive r, this point will be 3, comma. But then if r is positive, right? So here we have the pole, here we have the polar axis. This point is somewhere here. If r is going to be positive 3, then we have to represent it with the theta that goes all the way from the polar axis to the ray where the point is located. So theta couldn't be 3 pi over 4 anymore. Theta will be 3 pi over 4 plus pi. So then that means 3 comma 7 pi over 4. Now we need to know how to convert back and forth from polar to Cartesian, Cartesian to polar. And this is going to be the merge of the two planes, the Cartesian plane with the polar plane. So here you notice that I have drawn the typical comfortable Cartesian plane. But if I make a few assumptions, I can also try to somehow see the polar plane within the Cartesian plane. But again, this connection is going to be momentarily, just so that we develop some formulas, some equations that are going to allow us to convert back and forth. The two planes, they don't have to be within the same, they don't have to be identical, they don't have to be together. I'm going to somehow merge them right now just so that you see some connections, but then they're going to be separate once again. So imagine that I somehow take the origin as being both the typical origin and the pole. And imagine that I consider the polar axis sitting right here on the positive x-axis. So just for a moment, imagine that the polar plane is here together with the Cartesian plane. Now look at this point right here with Cartesian coordinates x, y. That means that this distance is x and this distance here is going to be y. Well, in the polar plane, this point would have polar coordinates r, theta. And r will be the distance away from the origin or the pole, so in this case r, and then theta will be the angle formed by the positive x-axis or the polar axis in this segment right here. Let me even draw this as an arrow, call it a ray. So that's my theta. Now using or drawing a right triangle and using right triangle trig, it is easy to see now that cosine theta is equal to x over r, which really means that x is equal to r times the cosine of theta. And this is something fantastic to have. Similarly, we know that sine theta is equal to y over r, meaning that y is going to be to r times sine theta. So this is going to be my second equation. That means that I already have the tools to convert from polar to Cartesian. In other words, if I want to go from polar to Cartesian coordinates, right? That means that if you're going from polar to Cartesian, you have the polar coordinates. In order then to get the Cartesian coordinates, you're going to use the fact that x is equal to r times cosine theta and y equals r times sine theta. Okay, so this is how you are going to convert back to Cartesian coordinate from polar coordinates. Now let's go ahead and explore how to convert from Cartesian to polar. If we are in Cartesian coordinates, we will have the point x, y. We will know x, we will know y. That means that we need to know r and theta. How do we get r and theta? Well, I want you to go back to your right triangle, right here, this right triangle. And I want you to notice again, let me actually write y here along the triangle. I want you to notice that we can use the Pythagorean theorem. We can use good old Pythagoras. Pythagoras says that r squared equals to x squared plus y squared. So that will be the way for us to transition to r. We're going to have that r squared equals to x squared plus y squared, and that's how we're going to get r, by taking the square root. And we need to get theta. Well, again, think of a trig equation that has both x and y, because this is what we know. If we're converting from Cartesian to polar, we know x and y. So I am thinking of tangent. tangent should be able to give me theta, because tangent of theta involves y divided by x. So these are exactly the equations that we're going to use to find r and to find theta whenever we need to convert from Cartesian to polar. The only thing is, though, that whenever you're working with tangent, as you did back in grade 11, grade 12, you're going to always have to make sure that you calculate the theta that is in the correct quadrant, the correct location. Because you know that sometimes, actually pretty much always within 0 and 2 pi, we can have two possible values for theta with the same ratio y over x. So we're always going to have to be super picky, super careful, and make sure that we're choosing the correct theta. The theta that gives you the point in the appropriate quadrant. Example 2 is asking us to convert the point 2 comma pi over 3 from polar to Cartesian coordinates. So this is a point given to us in polar form. So then that means that r is equal to 2, and that means that theta is equal to pi over 3. That point will be, let's see, pi over 3 right here corresponds to 60 degrees. Let me circle that. So, oops, wrong. Pi over 3 right here. And then r is equal to 2. So we're going to count two radiuses. So 1 and 2 right here. Here is my point. So this distance is 2, and this angle right here is pi over 3. We want to be able to find the Cartesian representation of this point. So what do we know? We know that x is equal to r times cosine theta. That means 2 times cosine of pi over 3. And we know that y is r times sine theta. That means 2 times the sine of pi divided by 3. So just quickly, I want to use my right triangles to figure out pi over 3, or if you have the unit circle memorized, you can go ahead and do that. So this is pi over 3. That means root 3, 1, and 2. So then cosine is going to be 1/2. So 2 times 1/2, that's going to give me 1. And then sine of pi over 3 is going to be root 3 divided by 2. That means square root of 3. So therefore, the point is going to have Cartesian coordinates x comma y, which are going to be 1 comma square root of 3. If you remember, square root of 3 is approximately 1.7. So if you imagine, for the sake of argument, having the Cartesian plane right here, if this was your x and this was your y, then the x value would be 1 and the y value would be somewhere here about 1.7, for instance. Okay. Example 3 is asking us to represent the point with Cartesian coordinates 1, -1 in terms of polar coordinates. In other words, we want to go from Cartesian to polar coordinates. The first thing that I want to do, however, is to locate the point 1, -1. I am going to let 2 marks be 1 unit just to give ourselves more space. So this is 1, this is -1, here is my point. Now I want this point represented in polar form. That means that I need to figure out r, which is the distance away from the origin to the point, and I also need to find theta right here. Now please know that theta, it's okay for it to be positive, but it's also okay to have a negative theta clockwise. Positive or negative, that's okay. as long as theta is in standard position. In other words, it's being measured from the positive x-axis or from the polar axis. In order to start the analysis, we know that r squared is equal to x squared plus y squared. Substituting, we know that x is equal to 1 and y is negative 1 squared. So then that's going to give us 2, meaning that r is going to be square root of 2. And that's how easily we can find r. Now, in order to find theta, we're going to use tangent. Tangent of theta is equal to y over x. And I know y, I know x. I know that y is negative 1, x is 1. So then that means that y over x is going to be equal to negative 1. Now, tangent of theta equals negative 1. This equation right here is satisfied for two thetas. One theta that lies in the second quadrant, and the one that we want, the one that lies in the fourth quadrant. So I will ignore this one, obviously. I'm going to go ahead and just work with the theta in the fourth quadrant. You can use your calculator to figure out theta, but I'm hoping that you can also remember all of your work from last year. Hopefully you remember that if theta is equal to negative pi over 4, this equation is satisfied. So I can immediately find a solution. Theta equals negative pi over 4. And as I said, a negative theta is totally fine. So therefore, a polar representation of this point will be the point square root of 2. That will be the radial length. And then the angular measure is going to be negative pi over 4. But let's say that somebody wants a positive theta. Let's say this red theta right here. So if you want a positive theta, you can easily get that positive theta. So another representation, I'm going to put over here, or square root of 2. Then you're going to say over here, 2 pi minus pi over 4. That really means that this will be the point square root of 2 comma 7 pi over 4. So honestly, any of these two answers is totally fine. You can provide one with a negative angle. You can provide one with a positive angle.